Hello everyone, I hope you are doing well. So in today's video, we're going to go through the 2025 VCE Maths Methods Exam 1. I just want to say congratulations to the class of 2025. No more methods. I hope you know both your exam 1 and 2 went well. And yeah, and just like always guys, if you guys want private tutoring in specialist methods, physics or chemistry, or have siblings or friends who are interested, you can always email me through this email. And so yeah, let's smash through this exam. Before we even start, I will really go deeply into this content, so the video will be long because I want to, hopefully this video helps next year students with the content. And yeah, so let's smash through this video. So let's do question 1. Okay, question 1 is a basic, beautiful question. It's always differentiation. Let y equals x squared cos x, find dy dx. Here, beautiful. Now look, we have two functions being multiplied, like two functions are getting multiplied to each other, yeah? This is using the product rule, yeah? So we let u, where this is going to be our u, and this is going to be our v. So u, in this case, would be x squared, and v equals cosine x. Beautiful. And of course, you derive both of them. So what's u dash? It's 2x. V dash negative sine x. Beautiful. And so the product rule, how it works is it's u times v dash. So these two get multiplied first. Let me write that first. So dy dx equals, so these two getting multiplied first, which is just going to give us negative x squared sine x. Remember, plus, so product rule says plus, multiply v times u dash, these two multiplied, which gives us 2x cos x. 2x cosine x. And that is it. That's very nice, this type of question here. Very, very easy. Beautiful. Let me just highlight that right there. Okay, done. Easy one marker there. Question B, so it says let f of x be this function. Find the gradient of a tangent to f of x at x equals a. Okay, so let's just understand what's happening here. They're telling us to first find the gradient of a tangent. Now, what does so basically the gradient of any tangent is known as f dash of x. What does this represent? When you derive, so when you get say you have a function, when you derive it, this basically represents the gradient. Remember, it gives you the gradient at any, for any tangent, yeah? At a certain point on f of x. Does that make sense? Like, it gives you the gradient of tangent, basically. So it gives you the gradient of a tangent at any point on f, basically, on f. That's what it is, if you think about it. That's what f dash of x basically represents. So imagine, look, it says find the gradient of a tangent of f of x at specifically the point 8. So you're basically just finding f dash of summing the point 8. So the derivative at 8. The gradient of a tangent at 8. Make sense? This is what we're basically trying to find. But they've just reworded it differently, of course. Beautiful, let's do that. Okay, first let's derive this. So f dash of x. So to derive this, legend, look. So it's a 6 here. The 6 is just a constant. I'm just going to leave it there. How do you derive root x plus 1? There's a quick method. So you can actually use, to derive any square root, use this quick trick. It's just very quick to derive any square root functions. Let's have a look at it. For example, when you're getting a function like d dx, when you want to derive, say, a square root function, look, something with square root and has a function inside, yeah? The derivative of it is going to be f dash of x over 2 root f of x. Does that make sense? Like, for example, let's do one as an example. If I was giving you, what's the square root of x squared plus 1? Like that. What you're going to do when you want to derive something like that is, can you see how the function inside, which is called, in this case, f of x, the derivative of it will be, you derive that in the function, so which is basically just 2x, over 2 root and f of x. You know how f of x is the inner function? Just rewrite the inner function. And that is it. That's how you derive any square root functions using this rule over here. Beautiful. So I'm going to use this rule to actually derive this very quickly. And use these rules. They are so useful, especially in exam 1. So let's do it. So what's square root, like the square root of x plus 1? So what I'm going to do again is I'm going to so put a division. I'm going to derive the inside, which is just going to be 1 over 2 root x plus 1. Rewrite the function and done. And so 6, like 2 goes into 6 3 times. So we can actually just write this as 3. Beautiful. We've derived that. And of course, deriving 5, which is the constant, is 0. Done. So this is our derivative. That will give you that 1 mark there. Then it's subbing in the 8. F dash of 8. So subbing in the 8. This is where the other mark comes in. So 8 plus 1 is just 9. And the square root of 9 is 3. 3 divided by 3 is 1. Very easy. That is your marks there. This is your answer. Is that okay? Very, very easy. The gradient of this function is 1. Beautiful. Question 2. Let g of x be a function defined where x is greater than -3/2, so that g dash, so the derivative function of it, is 1/2x plus 3, and we're also given an initial condition, probably because we're going to integrate. Yes, find g of x. So we're trying to find the original function g of x, so we have to integrate here. So let's do that. So to get g of x, legends, yeah, you need to integrate. So integrate 1/2x plus 3 dx. That's what we need to integrate. And it's very easy to integrate. Remember, when you integrate this, it's a log. So g of the x will be what? So you remember how to integrate this? You first do 1/, derive the bottom part, which is just 2, log e, and then rewrite the bottom part, 2x plus 3. Don't forget that plus c at the end, because it's a constant. And to get that plus c, it's subbing this initial condition, as we know. So because, let me write that. As we know that g of 1 equals 0, that means g of x will be 0. So this will be 0. And when you sub in x equals 1 into this thing here, log e, that'll be 5 plus c. And to solve for c, you bring that to the other side, will be negative 1/2 log e 5. Easy? Done. So now we've actually done all the work. Now we can rewrite the function in a nice form. So let me just use a different color. So g of x, the original function, of course, is 1/2 log e 2x plus 3 minus 1/2 log e 5. Easy. Okay. Now, of course, we can, you can, more simplify this, because you could take the half as a common factor. So it'll be log e 2x plus 3 minus log e 5. Now, what happens when these two logs are minusing? What happens when two logs minus? They divide. So we can write this as 1/2 log e. So let's do that. It'll be 2x plus 3 divided by 5. And that is it. This is your actual function. So I will just put this nicely here. So that's your original, that's your final answer, g of x. Oops, what did I do there? There it is, like that. And I'm just going to put it right on the right side. So beautiful. That's your answer there. Easy. Very nice, typical question. It's a very great question right there. Nothing too bad about it. Nice. 2 mark right there. Okay. Next question. Question 3. So if f from 0 to 2 pi, so this is the domain where f of x is 2 cos 2x plus 1. This is a beautiful function, just a really nice function. State the range of f. Very, very easy. Okay. So we know to state the range of for sine and cos. It's actually quite easy if you use this rule, where this is what it is. It's basically, it's the translation minus the amplitude, comma, doing the same thing, translation, but now plusing the amplitude. This is the rule that you want to use every time you want to find the range. It's very quick. It's right to the answer. So, for example, this case, yeah, what is our translation? Our translation is our 1 here, positive 1, minus our amplitude, which is 2. So 1 minus 2, comma, then doing the same thing. Our translation, which is 1, but now it's plus your amplitude, which is 2. And hence that gives us as a final answer, -1, 3 as an answer. Very easy. So we're going to highlight that one. Let me just highlight this one. Beautiful. Not a bad question. Very easy. Next question. Solve f of x equals 0. Now we are given a domain from 0 to 2 pi. Make sure. Yep. So let's write let's write this whole thing down here. Okay. So we have 2 cosine 2x plus 1 equals 0. And we're given that the domain is 0 to 2 pi. Now be careful, legends. We need to fix this domain. Can you see how the inside of our function is 2x and here is x? We need to make sure that they are the same. So how do we do that? We just multiply this x by 2. So look, it'll be 2x, yeah? Now, can you see if I multiplied this by 2, I need to multiply this number by 2, and I need to multiply this number by 2. So that'll be 0, that'll be 4 pi. And done, legends. Can you see how this is 2x and this is 2x? This is our domain. This is the one that we're going to actually be using to get our solutions, proper solutions. It's using this. Okay? And now let's solve it. So what we first do is get cosine by itself. Like, you know this one, bring it to the other side. So let's write that down. 2x. Oops, 2x, sorry. 2x minus 1. And then divide both sides by 2 to get rid of that 2 in front. Beautiful. Now, what we're going to do is, can you see how, in this case, cos is negative, yeah? When in which quadrants is cos negative? Well, we can straight away see that cos is positive in these two quadrants, so it has to be these two over here. These are where cosine is negative. Done. And we first need to also find the base angle. In this case, the base angle is going to be pi over 3. Beautiful. Now, what we're going to do is actually solve this. So let me write it. So make sure you start with the 2x here, because the inside here. So 2x equals, let's look at the solutions. Okay, so we're going from 0 all the way to 4 pi. So 0 is over here. So you go, you've reached the solution over here, yeah? This is right here. This is going to be pi. So it's going to be pi minus your base angle. So it'll be pi minus pi over 3. Done. That is one solution. What about this solution? What about this solution? It's just pi plus pi over 3. Done. Of course, there's more because we have to get to 4 pi. Yep, you've done that. Now you go more to the rotation, and then your reach here is 2 pi. Done. And you have to keep going because we need to reach 4 pi. Then you go, then this will be, 3 pi here. And of course, we have a solution here and solution, so it'll be 3 pi minus. So it'll be 3 pi minus the pi over 3, your base angle. And of course, 3 pi plus the base angle. And done. That is perfect. We've got all our solutions and we are done. We've hit the domain perfectly. Okay. Very nice. And we need to just simplify now. So that will be 2x equals 2 pi over 3. This one. This one will be 4 pi over 3. This one will be 3 times 8 pi over 3. And 10 pi over 3. Be careful, these are not our final solutions because we need to get rid of that 2. You remember, our solution is going to be x equals, yeah? Not 2x. So what we need to multiply is, the best way is to divide all by 2 or just multiply everything by half. So imagine multiply this by half, multiply this by half. Yeah, so it'll be x equals pi over 3. Because the 2 gets, you get rid of the 2. This will be 2 pi over 3. How many 2's go into 4? And this will be 4 pi, so 4 pi over 3. And this will be 5 pi over 3. Done! Those are your solutions. Very, very easy, tough question here. Nice. Sorry. That's all you're going to do. You write those answers. Done for 3 marks. Next question. Sketch a graph of f of x for this domain. Okay. Pi over 2 to 3 pi 2. Be careful, not this domain over here. Yeah? Make sure you do this domain. And label all coordinates with their coordinates. Okay, now this is not too bad. So what I'm going to do first is I'm going to start. How do I sketch these? I like to sketch them this way. The range is the most useful thing for, I think, sketching, because can you see how this is -1? I like to draw like a y equals -1 and that y equals 3, because these are like our minimum and our maximum points. So look, -1, I'm just going to draw a straight line that passes through that. Well, it's just a straight line like that. That passes through -1, and also a line that passes through 3. There. Yep. And also a line that passes through the translation. You know what translation is 1? Like y equals 1. Also like that. And beautiful. These are going to be our thing that is going to make our graph. We can easily see the graph nicely. So, you know how a cosine function, because it is a cos function, yeah? It's a positive cosine function. We know a positive cos function starts from the maximum and goes like this, yeah? Let's do that. So imagine it starts from 3, which is our maximum, our top part. And, oh, we need to also find the period. Don't forget. Well, the period in this case is, you know, do you remember it's for cosine and sine? It's just 2 pi over n. In this case, which is 2 pi over 2, which is just pi. Your period is pi. It means it takes pi, like, one cycle is pi, basically. So, look. So, this is your, so imagine, look, if you're drawing it like this will be pi. So, you know how we started from 0? We have to end at pi, yeah? Because this is the maximum point, yeah, pi. And of course, our minimum point has to be midway, which is here. And there it is. So it would look something like this, of course. You draw it like that, and it'll look something like this, and you keep going. Now, it's so ugly. I want to try to make it more nicer than this, to be honest, because that generally doesn't look like the best thing we can draw. We can draw probably better. So what I'm going to do is I'm going to draw this nicely like this, like a sign, like that. And then I'm going to break it apart. So like that. I'm just going to, and then draw another one. Like that. So like this. Like that. Beautiful. And what I'm going to do is just kind of bring these over here and then do this. Of course, I'm just doing it on an iPad. Normally, you just do it by nice drawing, but I'm just going to make these nicer. I'm just going to split this here. And I'm going to split this over here. So it will look like this. So this part over here, which is our maximum point, will go looking like this, like that. You see how that's nice? It's more smoother. And then this part will be, it will be going like this, and this part will be connecting this. Well, it's not the best connection, but it's doing the job, like that. You see how nice that's a nice cosine curve there. Done! Perfect! And you keep drawing them, yeah? You keep drawing them. Oh my god. Oh my. Like that, and then take these two and then just duplicate these right inside there. Oh, they're not nicely connected. Why is it making my life harder? Okay, Legend, you don't even need... Oh, sorry. You don't even need these anymore. These lines were just supposed to make it more nicer to look at. But now all we're going to do is just copy this whole thing. And I'm just going to duplicate them. There it is. Nice duplication. There it is, like that. Done. Perfect. Look, we've drawn 2 circles. But remember, that's just drawing them. Remember, you're only going to sketch them from here. Do you see this part? We're only sketching them from pi over 2 to 3 pi over 2, yeah? Which is basically from here, pi over 2, all the way to 3 pi over 2. So we actually don't need this part. Like, we don't need this part too. We don't need it. We only need that part right there. That perfect shot right there. Look, pi over 2 to 3 pi over 2. And don't forget, label the endpoints of the coordinates, which is quite easy. You can see that the coordinates are pi over 2, negative 1. And this one will be 3 pi over 2, negative 1. Well, that's quite ugly, but negative 1. Done. Very nice, easy question there. Beautiful. Alright, so let's go down to the next question. Question 4. The probability distribution for a discrete random variable x is given in a table below where k is a positive real number. Okay, should that k equals 10 or k equals 15? Very, very easy. A typical, VCAR question here. All we have to do, well, we know when we add all of these probabilities over here, they must be equal to 1. So what we can say is that we know, to show this, we're going to say that the sum, this means the sum, yep, the sum of all of those probabilities must be all equal to 1. So this is what we want to show. And so let's do that. So let's add all of these up and equate them to 1. So what is 4 over k plus 2k over 75 plus k over 75 plus 2 over k must be equal to 1. Now, can you see how these two have the common denominator, so we can add them up? So what's 4 plus 2? That is just, it simplifies to 6, yeah? So 6 over k. And can you see how these two have the same denominator? So what's 2k plus k? That is 3k. 3k over 75. And we can simplify, like 3 goes into 75, 25 times, yeah. 3 goes into this 25 times. It just froze for a minute. Yeah, so 25 times, perfect, and that must be equal to 1. And so we're basically gonna find the common denominator, which in this case is 25k. So I'm going to multiply this whole thing by 25k. Look, so 25k times this over here, so 6 over k, plus 25k times k over 25, and 25k times 1. Can you say I multiply 25k? If you're wondering where I got that common denominator, I just multiply those denominators together. Beautiful. And I can cancel out this k here. So what's 25 times 6? That's 150. Yep, that is correct. Yep, 150. And these 25s cancel out, so you're left out with k squared. And 25, k times 1 is just 25k. Beautiful. And let's bring everything to the left-hand side. So we get k squared minus 25k plus 150 must all equal 0. And let's factorize that. So two things that multiply to give me k is k times k. And two things that multiply to give me 150 in this case is, well, we know that the solutions are 10 and 15. So we can say 15 and 10. When we multiply 15 and 10, that gives us 150, and both have to be negative because negative 15 times negative 10 is positive, 150. And when you, what's negative 15 times k? That's negative 15k. And what's negative 10 times k? That's negative 10k. And you can see when you add those up, that's negative 25k, which is the middle value. So these are our factors over here, which in this case would be k minus 15 and k minus 10. Must be equal to 0. And so your solutions are going to be basically k equals 10, basically 10, and k equals 15. Very, very easy question here. Very nice. Perfect. Okay. Not too bad, not too bad. Okay, next question. Let k be equal to 15. Okay, let's make sure. Find the probability that x is greater than 1. Okay, so when x is greater than 1, we're actually looking at these probabilities over here, yeah? So greater, not equal to 1, but greater, which is just basically finding it's just equal to the probability that x equals 2 and 3. So make sure I'm going to write that down here. So it's basically the probability of x equals 2 plus the probability of x equals 3. And so what is the probability of x equals 2, legends? It is actually k over 75. So let's write that down there. K over 75 plus 2 over, so probability of x equals 2 is 2 over k. So we'll plus 2 over k there. Beautiful. And we know, remember that k was, they told us that 15. So let's sub in 15 to those values. So this will be 15. And here, this will be 15. Let's see if we can simplify. How many 15s go into, in this case, 75? Well, 2, 4. So if you do it like 4 times, you get 60. 5 times. So this goes into it 5 times. So 1 over 5. And can you see in this case, our common denominator is 15. So I'm going to basically multiply everything here by 15 to simplify it. Yep. So look. So what I'm going to do is 15 times 1 over 15. So 1 over 5 plus 15 times 2 over 15. And you can see that in this case, the 5s go into 15 3 times, and 15 cancels out with 15. So you're left out with overall 3 times 1, which is just 3, plus, that's just left out with 2 here, over your common denominator, which was 15, which is all equal to 5 over 15, which your final answer is 1 over 3 when you simplify it. So let's write that down. So your final answer for probability that x is greater than 1 is equal to, 1 over 3. 1 over 3. Beautiful. So let's highlight that part there. Not bad question. So nothing too bad right now. Okay, next question. So it says, find the expected value. That's very easy. So when we have a table like this, legends, what we just have to do is multiply the x values by their corresponding probabilities and add them. So like 0 times 4 over k, plus 1 times 2k over 75, plus 2 times k over 75. And you just keep on going like this, yeah? And that's how you can find the expected value, specifically for these kind of tables. So let's do that. So we can say that the expected value, and let's do that for the first one. Well, the first one's quite easy because it's just 0 times 4 over k. That's already 0. And 1 times 2k over 75 is just 2k over 75. Beautiful. Plus, then we have 2 times k over 75, which is basically just 2k over 75. Plus, then we have 3 times 2 over k, which is 6 over k. Okay, now can you see how these two have the same common denominator? So we can actually add them up. So what's 2k plus 2k? That's just 4k. We can rub this out. This and put that right in there. Beautiful. And now just remember subbing the k value. You remember how k equals 15? We need to sub it back in here. So imagine just replacing all those values with like 15 in this case. So this will become 15. And this one over here is 4 times 15. You okay with that? That's very easy. And let's simplify them. Like in this case, can you see how the things that both go in 6 and 15 is 3? So how many like 3's go into 6? That's 2 times. And how many 3's go into 15? That's 5 times. So that's what this simplifies. In this case, how many can you see how there's two things that like 15 goes into this and that? So how many 15's go into 15 is just 1 time? And how many 15's go into 75? That's 5 times. Beautiful. So let's write that down. And then you can see that they are actually common denominators. So what we have to add is we add the tops for 4. So basically 4 plus 2 is 6 over k. That's your final answer. Very, very nice. Okay. All right. Beautiful. Doesn't look too bad. Question 5. A very typical question. So we have this and we're solving it. And okay, let's walk through it. This is a very typical question. It's come up actually quite a lot in papers now. It's very easy. So let's have a look at it. So you've got this exponential in this case, and you're solving for x. And the way to do this, legend, is that there's a hidden quadratic in it. Let me explain. You know e to the 2x, like this one? Can we write it as e to the power of x all squared? Because we know it's the same as e to the power of 2x. Because remember, using your indices law, 2 times x is just e to the power of 2x, yeah? So I like to write it like that. Minus 2, like minus 8 times e to the x. Can you see how this is e to the x? So I'm just going to write it as just normally e to the x. Plus 7 equals 0. Now, can you see what I can do here is I can let u be e to the x, yeah? I can make u be to the x, and I can sub u into all the e to the x. Like, you know how this is e to the x? I can replace it with u. And can you see how it was all squared? So it'll be u squared. Minus 8. Can you see how that's e to the x? And what are we making e to the x equal to? U. U plus 7 equals 0. Look, so basically, it does look hard at the start. But if you break it apart, you would easily see this pattern. And actually, they can do it for so many things. They can make a quadratic in a sine function, like sine, cos, log functions. They can just, yeah, you need to look at this pattern. So beautiful. And now let's factorize it. So 2 things that multiplied to give me u squared is u and u. And 2 things that multiplied to give me 7 is 7 and 1. And both I have to be negative, because negative 7 times negative 1 is positive 7. And when you add these up, like, because look, negative 7 times u is negative 7u, as you can see. Then negative 1 times u is negative u, basically. And this adds up to negative 8u, which is our middle value. So basically, we've got our factors here, which is u minus 7 and u minus 1 equals 0. And we solve that. So that'll be u equals 7 and u equals 1. Beautiful. Is that our final answer? Absolutely not. You need to come back. We're solving for x, not u. So we need to replace. Remember, all the u's, replace them back with e to the x. Yep. So let's do that. So you know how this was u? This will be e to the x. So replace that with that. Equals 7. And the same with this one. E to the x equals 1. And then what we're going to do, legends, is, for example, this one here, to solve for x, you need to actually convert it into a log. So it'll be log base e 7. Beautiful. And the next one is just by observing what x value will make this equal to 1. It's 0. E to the power of anything in it. So e to the power of 0 for anything is always equal to 1. Yeah. Easy, everyone. So that would be x. Also, x equals 0. Of course, you can convert into a log like this. Also, you can convert into a log. And look, you can convert into a log 1x. Now, of course, log of 1. Anytime you have a log and there's a 1 inside of it, it's always equal to 0. So both solutions, that's how you can actually get them. Very, very easy question here. It's come up so many times, and I love seeing it because it's such an easy marker to really kind of put in your pocket generally. So let's have a look at the next question. Let g of x be, basically it's the same function where the domain is all reals, okay? The function g of x has exactly one stationary point, which is a local minimum. Find the largest value of a such that when g is restricted to this domain, it has the inverse. All right, this actually is not too bad if you break it apart, because they've actually given you every detail that you actually need. They've told you that, for example, that it only has one stationary point, and we can kind of, you don't need to know how to graph it, but just like make up a graph in your brain, like in your head, basically, in this case. So what I'm going to do is I'm going to do this. I'm going to draw what I would believe it would look like, yeah? I don't know how to graph it, but I'm going to, all you need to do is focus on the local minimum though, yeah? So what I'm going to do, legends, we know that there's a local minimum, so I'm going to say the local minimum's here, and this is what a local minimum looks like, yeah? Easy, everyone? And we know that the domain is all real, so it goes forever, yeah? Like this. It could go like this. I'm making it up, but maybe I'm going to assume it, making it up, something like this. This is a total rubbish graph, but it doesn't matter. But I'm here to explain what we're actually focusing on. Now, our goal, legends, is this is your g of x function. Making it up, of course. So can you see how it has one stationary point? It's just a local minimum. And it says, find the largest value of a such that when g is actually restricted to this domain, it has an inverse. Okay, for a function to have an inverse, yeah, it must be a one-to-one function, yeah? And how do we know it's a one-to-one function? You need to make sure that it passes the horizontal line test. Let's explain what a horizontal line test is. Basically what you want to do is you want to draw a horizontal line passing through your graph, yeah? And if the horizontal line intersects it more than once, like for example, look, can you see in this place, this horizontal line intersects it twice on this graph, big no-no. It's not a one-to-one. It's only supposed to intersect it once. Look, twice again here. Absolute rubbish, yeah? Now, there are two possibilities in how we can actually make this, we can absolutely, make, in this case, there's so many ways we can kind of restrict this function to make it a one-to-one. Now, one of the best cases is looking at the stationary point, because what we can do is think of it like this. There's two possibilities. If I, for example, in this case, cut this, yeah? Imagine you cut it in half. Then you'll be left over with two pieces over here. Do you see these two pieces? You have this piece here, and you have these pieces, yeah? Okay, easy? So what you can do then is, for example, what you can do is you can kind of rub this one out. Look, if you rub this one out, can you see how that right-hand piece, it's actually a one-to-one function because it does now pass the horizontal line test. Can you see how it's passing because it's always intersecting once? Those straight lines are intersecting the graph once. This is a one-to-one function. And that's one possibility. There's so many possibilities, yeah? Of course, another possibility was you could rub this one out, couldn't we? Now, this is also a one-to-one, yeah? Beautiful. Now, our case here is to look at it like this. They told us our domain is this, yeah? For our, where g is restricted in this domain. What do we think of, what would be a in this case? Well, can you see how they're telling us negative infinity to a? So we're only looking at the left-hand side, so like the left part of our graph, so this part, yeah? So forget about this rubbish over here. We don't care about that right part, but we're only caring about the left part. Does that make sense, everyone? So we're looking at this part over here. All right, and we're just finding the largest value of a, yeah? Because a could be anything. Couldn't you also restrict this from here to here? And also, isn't that a one-to-one function? Absolutely, yeah? But we want the largest value of a, yeah? And that largest value actually occurs in the stationary point, yeah? Does that make sense? This is your actual largest value of a over here, which is where the stationary point occurs, because if you go just above a, legends, big no-no. Because then, when you do the horizontal line test, you intersect twice. So it's actually just, the largest value of a is actually at the stationary point. And that's it. We want to find basically the x value for that stationary point, and that's our a value. Does that make sense? So to do this question, what we need to do is, how do you find stationary points? Of course, we know you have to derive this function, let it equal to 0, and solve. So let's do that. Okay. So what we're first going to do is we're going to derive g of x, the function, and of course that's easy. So you remember how to derive any e to the 2x. For example, you just derive the top part, which is just 2, and rewrite the whole function. So deriving exponentials is very easy. Same with this one. This will be just minus 8e to the x. And of course, you derive constants, that's just 0. And of course, we wanna make sure that g dash of x is equal to 0. So now we make this whole thing here equal to 0. And can you see how there's a common factor of 2 to the e to the x? So this will be e to the x minus 4 equals 0. And so, okay, of course, using the null factor law, so just make sure this is also in bracket, you'll get 2 to the e to the x equals 0 as one of the solutions, and e to the x minus 4 equals 0 as a solution. Now, there's a no-no here. What's the problem? This doesn't exist. Can you see, do you remember, any e to the x, any exponential is always greater than 0. It's not equal to 0. It cannot be equal to 0, and it can be negative numbers. So that's rubbish. This is the only one that we're solving as our stationary point. So bring the 4 to the other side, and of course find x by, it's going to be log e4. And that here is our stationary point. That is our x value for our stationary point, this x value over here, which is also known as a. So our a value in this case would be, let's write that down, our a value is just log e4. Very nice. Beautiful. Question, let's have a look at this. Question 6. Consider the binomial random variable. We have this beautifully. Find the variance. Okay, not too bad. So to find the variance of a binomial, remember, the variance of x is just np 1 minus p. Yep. So in this case, what's our n? Our n is our 6 in this case. It's the number of trials, and p is our probability of success. So it'll be 6 times 1 over 4. And then 1 minus p is just 3 over 4. Now, you can just multiply these two together. It's just 3 over 16. And keep out, these are both even numbers. So how many 2's go into like 6? 3 times. And how many 2 go into 8? 8 times. So it's 3 times 3, which is 9 over 8. And that is your variance of x. Beautiful. Very nice question. Not bad. So there isn't actually a lot of rubbish probability questions. They're actually quite nice. They're very straightforward, which I'm quite liking this. So the next question is, determine the probability that x is greater or equal to 5 and give your answer in this form, where a and b is an element of z. Now this actually is, I don't know which paper, but I remember there's a paper in VCA where it had these type of questions. They're not too bad actually. So if you guys do a lot of VCA questions, the more you do, the better you become in these type of questions, especially these hard ones. Okay. So we want to find the probability that x is greater or equal to 5. What is that? Let's go up. Now, legends, can you see how a number of trials is 6 here? Let's think about it first. I'm just going to draw a number line to represent what's happening here. So this is your number line. Remember, binomial means whole numbers. It means like, we're dealing with whole numbers, no decimals. For example, the lowest value we can have for the number of trials is 0, because it meant like 0 trials. We can have 1, because you know how it goes to 6, so we can have 1, 2, 3, 4, 5, 6. Beautiful. So these are our trials, and we're trying to find the probability that x is greater or equal to 5, which means it's basically equal, so greater, or equal, so we can equal 5 and greater than it. So we're just basically trying to find the probability of x equals 5 and x equals 6, yeah? That's what we're trying to find. So let's make sure we write that. We're just trying to find the probability that x equals 5 and the probability that x equals 6. Beautiful. And to do that, we have to use our combinations, our binomial formula, yeah? For example, in this case, it's how do you find the probability of x equals 5? Remember, so how many trials there are? There's 6 trials. That's your n. Choose, what are we finding? For example, we're doing with the 5 first. 5, choose 5. What's our probability of success? 1 over 4 to the power of 5, your x here. Then times by the probability of unsuccess to the power of 6 minus 5, which is 1. That's it. This is probably that x equals 5. And then we have to add it to this one, probably that x equals 2. So it's the same thing. So what's our number of trials? That's 6. Choose, well, we're using 6 here. 6, choose 6. The probability of success is 1 over 4 to the power of 6 in this case. And the probability of non-success is 6 minus 6, which is 0. Beautiful. Look at that. That's really nice. Now, of course, we know in this case, anything to the power of 0 is always equal to 1. Easy, everyone? And if you have a combination which has the same number at the top and the bottom, so like 6 choose 6, or 1 choose 1, or 2 choose 2, it's equal to 1 also. And we can also prove that if you're kind of confused, you can use something called Pascal's triangle. It's one of the best ways to determine, to simplify a combination. Like, look, I'm just going to draw. So 1, 1. You just draw like 1, 1, like this beautiful pyramid here. And then all you're going to do is add these two up. 1 plus 1 is 2. Then that's going to be 1, 1 again. And you do the same. These two add up. So what's 1 plus 2? That's 3. And the same with this. 2 plus 1 is 3. 1, 1. And you just keep going. That's then that's 4. Then that's 6. That's 4. That's 1. That's 1. And you do that 5. That's 10, 10, 5, 1, 1. And I'm going to show you why. And then you do it. So 6, 15, 20, 15, 6, 1, 1. Why is this so useful? It's because it's actually going to help us determine all these combinations. Like, for example, what is 6 choose 6? 6 choose 6 means this 6 at the top is we're going to go like down by 6. Like, for example, can you see how this has 2s? This row has 2s. This row here has the 3s. This row over here has the 4s. This row over here has the 5s. This row over here has the 6. Look, this is our 6th row. And of course, this has to have 1s here. So this row has the 6, so we're going 6 down, and we're going to go 6 to the right. We have to always start at 0, remember? So this is your 0. 1, 2, 3, 4, 5, 6. So you know how we went 6 to the right? Because the 6 means going right. It's equal to 1, because that's what we went. How easy is that? So this whole thing here, very nicely, we can just say it's 1. Can cancel out. Okay, what about looking at this example? 6 choose 5. Let's do that one. Look, same thing. Look, we're looking at 6 means 6 down, and choose 5 means you're going to look at 5 times. So that's 0, 1, 2, 3, 4, 5. That simplifies to 6. So let's make sure we have that. So this here, nicely, will be 6 in front. Very easy, very nice when you're doing this. And of course, in an exam, you'll do it quicker, but it's very nice, yeah. And what I'm going to do is I'm going to simplify them. Like, for example, like, 1 to the power, like 1 over 4 to the power 6, I can break down into, like, simple terms. Like, for example, this 6, I can multiply with the 1 and I can multiply with the 4. So I can represent this as 1 to the power of 6 over 4 to the power of 6. So much better like that. And we know 1 to the power of anything is just 1. That's 1. So we can look how nice that simplified it for us. Because this is going to be more useful specifically for these type of questions. Like, for example, here, what I'm going to do is, okay, kind of do the same in this case. Like, okay, this is just 3, like this one's useless because it's just 3 over 4. Like in this case, I'm going to break this down like I did with this one over here. So what's going to be 1 to the power 5 over 4 to the power 5? 1 to the power of anything again is 1. So this here, we can actually represent it as 1 to the power 5. Easy? So like that. Okay. And look at this. Can you see how these two are multiplying? 3 times 1 is just 3. So that'll be just 3 over. And can you see how this 4 to the power 5 times 4 to the basically power of 1? When two of the same bases get multiplied, their powers add up. So so basically 5 plus 1 is 6. So this will be 4 to the power of 6. Beautiful. Look how nice that simplifies to. And don't forget that 6 that's being multiplied. So imagine like you multiply 6 here, legends. So 6 times 3 is 18. Put an 18 there. Done. And what we're doing here is we're taking that and we're adding it with this. And can you see how they have the same denominator? So we can add their tops. So it'll be 19 over 4 to the power of 6. Of course, that's not your final answer because you need to get it as 2 to the power of b. And that's actually easy. Like, for the 4 to the power of 6, yeah, this bottom part, we need to convert it in terms of 2. Can we say, 4, yeah? Can we write it as 2 squared? Isn't that 4? And you know how it's all to the power of, like, 6? And we know by using indices rules, 6 times 2 is, you can simplify this as 6 times 2 is 12. We can write it as 2 to the power of 12. You see how that becomes so much nicer? 2 to the power of 12. And guess what? We've got it in this form. You see A is 19 and 2 to the power of B is 12. Very, very nice in this case. So your final answer, I didn't show a lot of working out, but I mostly robbed it all. But of course you want to show working out in an exam. So probability that x is greater or equal to 5 is equal to 19 over 2 to the power of 12. Okay. Not a bad question. 2 marks. Okay. Is that it for this question? Beautiful. Let's do the next question. Question 7. Let f be have a domain of all reals, and this is f of x, which is just basically a cubic function. Verify that x equals 5 is a solution to f of x equals 0. Very, very easy question. All we do is try to sub in 5, and if it does equal to 0, this function, then it is a solution. That's how you kind of prove these type of questions. So let's do that. So what we just need to do is that when we sub, because if we're trying to check that, when you sub in x equals 5, so when you sub in 5 into the function, if it equals 0, then it is a solution. So we just need to double check that first. So what is f of 5? So if I do that, so it'll be basically 5 to the power of 3 minus 5 squared minus 16, 5 minus 20. Okay, 5 to the power of 3 is 125. 5 squared is 25. 16 times 5, just doing that there, because I'm not gonna, 5 times 6 is 30, 5, 6, 7, 8, 80, so that's 80, so that'll be minus 80, and then minus 20 here, don't forget that minus 20, and done. And let's see if that actually equals 0. And you can see 125 minus 25 is 100, and negative 80 minus 20 is also negative 100, and of course that equals to 0. And it is actually, that proves it. So we know that when we sub in 5, it does equal to 0. Hence, this is a solution. This is an actual solution. Very easy, typical question. So you need to show this working out over here to get those marks. All right. Express f of x in this form where d is an element of all real. So what's actually happened here is that they want you to factorize it in this case. And guess what? They've actually given you the hint. Because if fate, like I'll show you, if fate didn't give you any hint and you just have to factorize it, unfortunately you just have to kind of sub in values like 1, negative 1, and then use like the factor law, like the factor law just to check which one is a root and a solution, and then you have to use some long division and all that work. But luckily here they've given us a root or a factor that works already. Can you see here that f of x can be expressed as this, and can you see how they've already given us a solution, x minus 5? So this is actually our factor, and they've actually been really nice to do that here. So look, this here is already a factor. You see, this represents a factor. Now I'm going to show you 2 ways different schools approach it, and I think some people, some schools use the long division and some use something called synthetic division. Now I believe specifically these type of questions use synthetic division. It's such quick. I'm going to show you both ways because better, and choose which one you would like to use in an exam. It's better to know both of them actually, because some are more useful than others in such cases. So this is our factor, and of course to find the root legends, all we have to do is we solve this equation, in this case like x minus 5, we solve it to equal 0, and that's just going to give us x equals 5. This is what we call a root. Can you see how it's like x equals? This is called the root. So let's look at the 2 cases that we can work with. How can we then do the division and stuff? So let's first use something called synthetic division. And synthetic division works by this. So you draw like a normal long division table like this, and what you do is what you sub in here is actually the root, not the factor. In long division, normally you would sub in, like you put the factor, but we just put the root. So you know how it's x equals 5? You just put the 5 in there. Beautiful. And what we're going to put here is, we're not going to put the whole function, this whole function over here. We're only going to put the coefficients. Like, can you see how the coefficient of this is 1? The coefficient of this is negative 1. The coefficient of this is negative 16. The coefficient of this is negative 20. Like that, we're just going to put the coefficients. So let's write it. So this one's 1, negative 1. What was the other one? Negative 16, negative 20. Beautiful. And here it is. Let's look at it. So synthetic division, the way it works is so quick. What we do is for the first value, which is 1, we're just straight away going to put it down. Nothing happens, just straight away put it down. Look. And look at the steps, how easy it is. What's 1 times 5? It's 5. You put it over here. And then you add these 2 values. What's negative 1 plus 5, guys? That is 4. Yeah? And to do the same thing again. What's 4 times 5? That is 20. Then what's negative 16 plus 20? That is positive 4. Then what's 4 times 5? That's positive 20. And you add these up, that's 0. And this here, the last thing, is called your remainder. And this is the beauty of it. It's actually it's made your life so much easier, because now the factor of this whole thing, you know how the factor was x minus 5? This actually gives you the coefficient of the quadratic. You know when you factorize this, when you factorize it, you'll get, of course, it's going to be a quadratic. So this is the coefficients of the quadratic. Like, can you see how the first one's just 1? That's for the x squared. So it'll be x squared. Can you see how the 1 will be here? So it'll be by itself x squared. Then you know how the 4x, you write 4x here. And then the constant, which is plus 4. And look how beautiful that is. Simplified nicely. And so we've got it like this now, yeah? What we can do is, remember, we want our thing to be x minus 5. And this here actually can be factorized, of course, just by looking at it. When you factorize, it's just x plus 2 squared. So you can actually just make, when you factorize this, it's just straight away x plus 2 squared. And that's it. Easy. So f of x overall can be represented like that, yeah? You see how easy that is? That's how you can represent your new. So f of x is x plus 2 squared, x minus 5. Is that correct? Did I get that? Beautiful. That's it. So that's how you use synthetic addition. Of course, you can use long division. But long division works by this. It's using the kind of the same table in this case. Look, you use the same table. But what we do here is we put the factor. You know how the factor in this case is x minus 5. And then, you put the whole equation in it. So like x to the power 3 minus x squared minus 16x minus 20. And so let's work through it. Synthetic division works this way. So think of it like this. X to the power 3, yeah? So x to the power 3, when it's divided by x, what do we get? We get x squared. Isn't that right? So look, x to the power 3. So this first value, yeah, which is in this case x to the power 3, it's being divided by x. Like the front of x, can you see that will just give you just x squared? And you put the x squared on the top. Easy? And then what we do is expand. X squared times x is what? That's x to the power 3. What's x squared times negative 5? That'll be negative 5x squared. Easy, everyone? Very easy. Look. And then what we do then is we minus them. So what's x to the power 3 minus x to the power 3? That's just 0. So no. And what's negative x squared minus negative 5x squared? So look, what's negative x squared minus negative 5x squared? That's just negative x squared plus 5x squared, which in this case is 4x squared. Very easy. You see how easy that is? And then what we do is after doing that, we put the next value down. So this value, negative 16x, we just put it over here. And we do the same step. So what's 4x squared divided by x? 4x squared divided by x. You can cancel that. It's just 4x. And do the same thing. 4x times x is, in this case, going to be 4x squared. And what's 4x times negative 5? That is negative 20x. And you minus. Same thing. See? Okay. So look, 4x squared minus 4x squared is always 0. And what's negative 16? So negative 16x minus negative 20x. It's just negative 16x plus 20x, which is basically 4x. And then you put the next value down, yeah? Negative 20. And the same thing, yeah? What's 4x divided by x? Is just plus 4. And then you expand. 4 times x is 4x. And 4 times negative 5 is negative 20a. And then you minus. And of course, if you minus this whole thing, this will be left over at 0. And that's your remainder. But at the end of the day, look, this is all we wanted. This over here. Look how easy we factorize it. And this is the same step, but this made our life so much easier, just quicker. Do you see how quick it is? And yeah, choose your whatever you find better. But at the end of the day, you should get the same answer. Really nice. Not too bad. Beautiful. Next question. Consider the graph of fx now and complete the coordinate pairs with the axial intercepts. Alright, so the x-intercepts, okay, they've given like templates so we can sub in the values. That's not too bad. For example, let's find the y-intercept first. To find the y-intercept, we've got the function here, and if you sub in x equals 0 to all of them, these all become zeros, and you just left out with negative 20, yeah? So we can straight away sub in here. Negative 20, like that. Okay, for the x-intercept is really easy. We use the factor, this factor here. When you solve this factor, you get two solutions, of course. You get the x equals 5, and the x equals negative 2. Sorry. Negative 2. Now, of course, for the negative 2, because it's squared, it's going to be reflected, yeah? Like, for example, can you see how this is... like this one, can you see how this one passes through the x-axis? This one is reflected. So, this one is the negative 2 in this case. Negative 2 right there. And this other one has to be L5, of course. Easy, because it passes nicely. And that's it. Beautiful, beautiful question. Really easy. They've actually given you a nice template here. Not bad. Let's look at the question. Let g be a function which has a domain of Orioles and g of x is x plus 2. State the coordinates of the stationary point of inflection for this graph, f of x times g of x. Okay, let's do it. So we're just multiplying the functions, basically. So you know f of x was Let's use a factors form. X plus 2 squared. X plus 2 squared. X minus 5. Just let me double check that if that's the same. Okay. And then you're multiplying g of x, which is just, again, x plus 2. Can you see how this is perfect? X plus 2 squared times x plus 2. These are just going to be x plus 2 to the power 3. Because they're the same thing. Beautiful! Now, I know for a fact that you can draw this, because this is very easy to draw. So if you want to draw these, this is what it looks like. So, you find the x-intercepts first. So let's do that. Well, we know that there's going to be an x-intercept at 5. And we know that there's going to be an x-intercept at -2 for this one. But can you see how this is to the power of 1? So and it's positive. This whole thing's positive. So it's going to pass like this. Like, look, it starts from the top right. Like, top right. It's going to pass through 5 perfectly. But you know how this is cubed? Because it's cubed, it's going to have like a stationary point of inflection when it passes through -2. So you know it's going to go like this. Then it's going to bend like this. Do you see? Like a point of inflection. Do you see how it's bending like that? And done. So in this case, they're just telling you, hey, start the coordinate of the stationary point of inflection. We know our stationary point of inflection is occurring at this coordinate, which in this case is -2. Let me write down another color, which in this case is -2, 0 as the coordinate. Very easy. Okay. Next question. Write down the values of x for which f of x times g of x is greater or equal to 0. This is a very typical question. I've seen it quite a lot now. If you've done quite a lot of exams, specifically in the newer study exams, they've always come up and it's so easy to deal with them. So let's have a look at them. So what I do is I kind of break it down into two functions. Like, for to solve an equality, specifically in these cases, the f of x times g of x, I'm going to just label it as the color orange. And I'm going to label purple as the other side, which is the y equals 0, yeah? So, and I'm going to take the graph, the graph that we've drawn here? I'm going to take it. So can you see how how f of x times g of x, the function is in this case, can you see how it's the orange graph? And I'm also going to draw a y equals 0 graph in a purple color. You see I'm drawing that in a purple color? Like that. Beautiful. And then I'm going to take this, I'm going to show what we're going to do. We're going to use this to help us solve this inequality. What this inequality is saying is, think of it like this. When is the orange graph, can you see orange graph? Greater or equal, so bigger than the purple graph. So bigger or means larger, like taller basically in this case, yeah? So in which are the values of x basically, where in this case what we're talking about is the orange graph bigger, so taller than the purple line. And we can straight away see it's from here. So it's from here. Do you see that? Can you see how the orange graph is bigger? It's taller. Do you see how it's, look, as you can see in comparison, look, can you see, looking at from here and here, look from, you can see how the orange is bigger, like it's taller in terms of the y values compared to our purple line, which is in this case 0, yeah? So from that, and also from this point, yeah, can you see how also from this point, it's also taller? Perfect, but not in these values, because you can see that the purple line is actually taller. It's above the orange graph, yeah? So these are x values, yeah? So nicely, these are x values where the ones that are highlighted in red is where the f of x times g of x is greater or equal to 0. And so let's write the x values. So we can say it's an x is an element from where? Well, we can see how we were going to -infinity. Do you see how it's going to -infinity? All the way to the point -2. Now, do we include -2? Absolutely. Can you see how it's saying greater or equal? So it can actually equal 0. When they're equating this, that's that 0, y equals 0. Can they equate? Absolutely, they can. So we're going to make sure you put a square bracket, union, and then we have from 5 all the way to positive infinity. Like that. Is that easy? Very, very nice. So typical types of questions that's come up quite a lot now. And yeah, very easy to get full marks for these type of questions now. So question 8 says, consider this function here, which is the continuous random variable x, has a probability density function f of x. Find k such as the probability that x is greater than k equals 9/16. One of the most typical types of questions. Very easy. Whenever exam 1 specifically has all the ways these type of questions, which are probability density functions. So the way I work through these type of questions is to first I make a fake graph. Now you don't actually need to really graph this, because you can just make a fake graph and you can work through it. because it's like they all follow the same thing. Let me explain. Like, for example, you can kind of just graph this. You can make up, like, for example, let's say this is just an axis here, and you can just make up like a, let's say, look, this is the graph of it, something like this, where this here is your 0, because you know how you're going from 0 to 4/3. Make that 0, and this here point is 4/3. Makes sense? And of course, we know that the area under the graph has to equal 1 because it's a probability density function. Remember that, yeah? Now, what they're saying is find k such a probability that x, that's greater than k is 9/16. What that means is k is between this 0 to 4/3, somewhere here. I'm making it up. Let's say it's over here. So basically what they're saying is this probability over here, well, let me draw it nice on my, so this probability over here is equal to 9/16, yeah? So we actually have to use integration to get that. So we have to solve for k, yeah? Because we know that area has to be equal to 9/16. So what we can say is this. We can say that the integral from k to 4/3, yep, so you look, so from the k to 4/3 of the function f of x, which is this whole function here, so 3/8. Now this 3/8, you can see this 3/8 is just a constant. You can actually just straight away take it out of the integral to make your life easier. And then it's just for minus 3x dx, this here. Beautiful. And what we're doing is basically integrating that. And we know this whole thing is going to be equal to 9/16. Yep, easy. And we're just basically going to integrate this and solve for k. All right, so what I'm going to do is, first of all, this 3/8, actually can get rid of it. Because if I multiply both sides by 8/3, the reciprocal of this, can you see how these 8s cancel out? All of them cancel out beautifully. So this will disappear, the constant. And what, wait, so how many 3s go into 9? It's 3. And how many 8 go to 16? It's twice. So this actually just equals to 3/2. It just simplifies to 3/2. Done. And let's just integrate this. So how do you integrate 4? Integrating 4 is just 4x, of course. How do you integrate, negative 3x? It's just 3x²/2. Close it from k to 4/3. And that's all equal to 3/2. Beautiful. Now what we're going to do is sub in 4/3, the top terminal inside the function. Let's do that. So what's 4 times 4/3? Minus, okay, this is ugly. So imagine subbing 4/3 to this whole rubbish. We'll do it on the side. So it's -3, and you're subbing 4/3, and it's all being squared, divided by 2. So, okay, first of all, what's 4 squared? 16. 3 squared is 9, so this becomes 16/9. And 3 goes into 9 3 times. So it's just -16/3, so we can write that nicely, -16/3. Okay. We don't need that negative, by the way, because the negatives, sorry, why did I put the negative? The negatives, we've already put it here, that negative. So what's 16/3 divided by 2, which is just the same as times a half. 2 goes into that 8 times. So it's 8/3. We can write this as 8/3. So that simplifies like that. Rub that rubbish out. Ugly. Okay, done. So we've done that. And what we can do is close that bracket out. And of course, 4 times 4 is 16, like 16/3. So let's write that. 16/3. And can you say, oh shit, the denominators are the same, so we can actually minus them. What's 16 minus 8? That's just 8/3. Just this whole thing becomes 8/3. Done. Then we're going to minus this whole thing by now subbing k into it. So k into this whole thing, which is 4k minus 3k²/2. And close that bracket like that. Done. And so what we're going to do is, of course, expand it. So like negative times that is -4k. And negative times that is positive 3k²/2 equals 3/2. Now, can you see how the common denominator, and there's no common denominator, but like, because there's a common denominator of 3 and 2, what is that? It's just 6, because you could just multiply them. It's 6. Imagine multiplying the whole function by 6. Imagine doing that. That's what I'm going to do, actually. So, like, if I multiply, like, imagine, if I multiply this by 6, 3 goes to the 6 twice, so this will be 16. In that case, I think I might just over confuse a lot. So what I'm going to do is, I want to do a quick, but I want to show you guys what I'm going to do. Yeah, so what I'm going to do is I multiply, because the common denominator is 6, so 6 times this function. I'm going to multiply everything by 6. Don't forget that minus 6 times 4k plus 6 times 3k²/2 equals 6 times 3/2. Can you tell I just multiplied 6 to everything? And so how many 3's go into the 6? Twice. So that'll be 8 times 2, which is 16. What's negative 6 times 4k? It's 6, 12, 18, 24, so it'll be negative 24k. How many 2's go into the 6? It's 3 times, so 3 times 3 is 9k squared. How many 2 goes into the 6? That's 3, so 3 times 3 is equal to also 9. Beautiful. And I'm going to bring everything to the left-hand side. So it'll be 9k squared minus 24k plus 16 minus 9 equals 0, which is 9k squared minus 24k, which is plus 7 equals 0. All right, so we've got this, and we want to factorize this. So what 2x multiplied to give us 9k squared? It's like 3k and 3k. Cross. And what things multiplied to give us 7? Like negative 7 and 1, basically, just these. And so so what's negative 1 times 3? That's negative 3. What's negative 7 times 3? That's 7, 14, 21. So negative 21, basically, k. Oh, that perfectly gives us negative 4k. Done. So that's actually our factors. So let's put that there somewhere here. We get 3k minus 7. 3k minus 1 equals 0. So our k can be equal to 7 over 3. And our k could equal to 1 over 3. Now, be careful. We need to check if they make sense. Like, for example, we know that the k value is between 0 and 4 over 3, like what we said. Well, 100%, 7 over 3 is bigger than 4 over 3, yeah? Does that make sense? So this is actually rubbish. This is wrong. You decline this one. Because what we say is, we can say that k is between 0 and 4 over 3. So your only final answer that's actually realistic is k equals 1 over 3. That's between that, yeah? So you would say your final answer is 1 over 3. Okay. Not bad, not bad. Okay, so done. Next question is, the function h is a transformation of f of x such that, so you know function h of x is just f of x that's been transformed to make it. And it says the h of x is just basically m times f of x plus n, where m and n are real numbers. Then what is the integral from 0 to 4 over 3 of h of x dx in terms of m and n? Not bad. So what we're going to do, legends, is do this. I'm going to write this integral from 0, look, can you see it's 0 to 4 over 3 and h of x. Now we know h of x is just this function, so we're just going to write this function, replace that, just write it in terms of this function, m f of x plus n dx. And what we can do, remember in an integral, one of the integral properties is we can expand that integral, yeah? So what we can do is expand that integral, so to 0, 4 over 3, so it'll be m f of x, so that's one integral, I can break it down, plus the same thing, so from 0 to 4 over 3, and dx. Can you see how I just broke down the integral? And you know how this is a constant? M's a constant, so we can just take the m out, yeah? It's a constant. Aha! If you know what you know. Look at this. 0 to 4 over 3 of f of x dx is what? Remember how f of x is this function, yeah? F of x is this function. We're saying, what is the integral of 0 to 4 over 3? 0 to 4 over 3. What is the area? Integral means area under the graph. Well, 100% it's 1. Remember, it's a probability density function, yeah? Easy? So this here is just, this whole thing simplifies to 1. Does that make sense? 1. Easy? That just simplifies to beautifully 1. And then you've got this leftover, and of course we have to actually, unfortunately, do more work here. Like that's going to be like then m plus, then we need to integrate n, which is just, of course, n of x from 0, 4 over 3. And what we do is we sub in that 4 over 3 first, so it'll be 4 over 3 n minus, then doing the same, but if you sum in 0, it's just 0, so you're left out with this. And that's your answer, legends. This is what it's actually simplified to. So you can just leave it like that straight away. I don't think, yeah, you can leave it, or you can simplify as a common denominator. It doesn't matter, basically. So what it is, so for integral from 0 to 4 over 3 of h of x is actually just dx equals to m plus 4 over 3. And very nice. Actually, that's a very nice question. Very nice. Okay, that's nice. Done. Question 9. Is this the last question? Because I'm feeling drained right now because it's quite late. It's late at night right now. Consider question 9. Consider the functions where, you know, where it has a domain of all reals except 1, and it's basically you can see that this is actually a truncus, yeah? Beautiful. And then we have a domain for G, which has a domain of all reals, and it's a quadratic, you can see, where w is a real number, if w is equal to -3, find 4 solutions to f of x equals g of x. Easy. So what we're doing, legends, is just equating them. Yeah. So look, what is so f of x, which is w squared over x minus 1 squared, and we're just equating it to x minus w squared. Can you say we just equated them? Now, of course, replace the w with -3 because they told us. So if you put -3 here in this one, because it's being squared, it's going to be positive 9. And you put -3 here, it'll be positive 3 here. Because like, do you see it? Like it's negative 3, it's positive 3, yeah. Beautiful. And you know this x minus 1 squared, we can just bring it to the other side, like multiply on the other side. Like that. Beautiful. And I think, look, there's a, to do this type of question, there's a quick method and there's a very long method. Of course, the long method is just expanding it. It's just a waste of time. Not really useful, actually. But if you see what I see here, what we can do is, can you see how these two are getting multiplied and they are squared? They both have that same power. Well, what we can do with them is we can put them in the same, think of it like this. You know when you get something like this? Like, if you got something like x to the power of a, I'm just trying to think how would yeah, like, I want to give a good example to give you guys. Like, how would I explain this? Because I'm actually really like, what the hell? I'm already, my brain is fried right now. Man, let me just do it. Yeah, man. I was just trying to figure, like, I don't know, I just felt a whole frozen. Okay, legends. So what's happening here is you can see how these have the same power, yeah? What we can do is, because they have the same power, we can put like them all in one. We can put them, the insides, this inside, all in one, because you know how they're all to the squared? So we can make them just x plus 3 and x minus 1 squared. Do you see? So this is the same as the top part here, because, like, think of it like this. Like, you know when you get something like x to the power of a and times, let's call that, that's actually, just trying to think. I'm trying to give a good example, but I'm tweaking for some reason. Let's say a to the power of, like, I don't know, like x, you know, and no, this is, say, yeah, a to the power of 2. And then imagine that's that part, and then you're multiplying it by a to the power of 3. And then they're all, oh my god, what am I doing? No, just say a, yeah, just a. So a to the a, and then it's getting multiplied like, so imagine that's a squared, and that this one's like b squared, yeah? Can you see it's the same thing, actually? Yeah. This is a good example. So that's like our a and it's being squared times b squared, yeah? What we can do is, because they have the same common, you can see how they have the same power, we can take that power, put squared, and multiply both of them, these two. And that's what's actually happening here, because remember, by indices law, this 2 multiplies by this, times this, but the 2 can multiply with this, and can you see how it's just the same thing? So yeah, putting them together can make your life so much easier. And I think that's the trick to this question, because if you expand it, you can still get the right answer, but it's such a long process. Okay, so then what we do, legends, is, as you can see, this 2, yeah, we want to square root it, like get rid of that 2, yeah, that power of 2. And how do we do that? We take the square root, so we get plus or negative square root of 9. And we can get rid of this rubbish. Done. Okay. We get that done. And of course, the plus or negative, what's the square root of 9? It's 3. Done. And of course, we have 2 solutions here. So what we can do is we have 2 ways to approach this. Of course, we use the positive 3 as one of the things. So for, first of all, let's expand this, man. Why are we leaving this like that? First, let's expand it. So expanding that will be like x times x squared. X times that is negative x. 3 times x is 3x. And 3 times that is negative 3. So that will give me, so I can replace this with x squared plus 2x minus 3. Perfect. That's better. And so let's look at the both 2 ways we can approach this. Question 1. Okay, so let's use the positive 3. So 3 equals x squared plus 2x minus 3. And of course, the other way is using the second, so the second is using the negative. So negative 3 equals this whole thing here. Okay, come on. Beautiful. So let's look at this process here, the first one. So you know what I'm going to do? This 3, I'm going to bring it to the other side. So it'll be minus 3 on here. And that'll be just minus 6, basically. Equals 0. And then we solve this. Now, can we... like in this case, can we can we factorize this? Yeah, we can factorize it just by looking at it. So we have to actually use the quadratic formula. So let's use that. X equals, like, you know, negative b. So what's our b? It's 2 plus or minus b squared, which is in this case 2, which is squared, it's 4, minus 4a is 1, and c is negative 6, over 2a, which a is 1, so it's just 2. That's equal to negative 2 plus or negative 4, 6, 12, 18, 24. So it'll be plus 24. That's this question, this is 8. This question's already tweaking. No, you know, it's just, yeah, it's so much work. Yucky. So 4 plus, and that's 28. And then, you know, it's being divided by 2. Okay, so 28 can be represented by, like, you know, it can be represented as like 4 times. So we've got 4 times 7, yeah. 7, 14, 21, 28. Beautiful. So which you can write as 2 root 7. 2 root 7. And so can you see how there's the 2's can cancel out? So it'll be negative 1 plus a negative root 7, because these two can, you know, these two all can cancel out. And yeah, those are already 2 solutions. Do you see that? And yeah, perfect. And because those are 2 solutions. Do we have any restrictions? Nah. Yeah, those are already 2. We have to also solve this one. That's already 2 solutions. Perfect. Just be careful with the algebra, and let's do this one here. So this one, same stuff. Like, you bring the other 3 to the other side, there'll be 0. So this one's actually okay. This is even much quicker. 0. You can see how there's x as a common factor, so it'll be x plus 2 equals 0. So we get 2 solutions, which is x equals 0 and x equals negative 2. And highlight that as the answer. Can you see that's 4 answers? That's perfect. That's what they wanted, didn't they? But what are the 4 solutions? And we've absolutely got them. So next question, which I think is the last page, which is so good. Let's just finish this paper. Consider the case where w is greater than 0. Okay, just remember coming back. Okay, if w is greater than 0, let's think about that. Find in terms of w the coordinates of the minimum turning point of this graph. Okay, so that you can straight away see that this graph is just basically a parabola, yeah? It's just a normal parabola, so let's just draw a normal parabola like this. Look, just a normal parabola like this. Okay, where it has an x-intercept at 1 and an x-intercept at w. Now, because we know w is a positive number, it's somewhere around here. It's in the positives, you know. Now, it could be here, or it could be over inside here. It doesn't matter, actually. Let's just put it w over here. And what we're going to do, legend, it is a minimum turning point, because when you expand this quadratic, it's x squared. It's the positive x squared. So it's going to nice to pass through these two like that. See how perfect that is? Like that. Beautiful. Done. This is how the quadratic is going to look. Now, okay, we want to find the coordinates of that minimum turning point. So this turning point over here. Now, guess what? It's actually not as bad as you might think, because if we have the 2x coordinates, yeah? These 2x coordinates, we know that if you have the 2x-intercepts, the turning point is the midpoint between those two. So what we can do in this case is do this. We can add, so you know how we know w is the x-intercept here and the x-intercept here. So we know that the midpoint between these 2 x-intercepts will give you the x value for our turning point. So how do you find the midpoint? Easy. You just add those values and divide it by 2. So for example, this one's w plus 1. So you add those values. And don't forget you divide it by 2. And so this here is your x-intercept of your minimum turning point. And of course, to find the y value, you have to sub it back into the original function. So let's do that. So you know it's y equals, we sub in that x, which is w plus 1 over 2 minus 1. And then it's w plus 1 over 2 minus w. So let's simplify that. W plus 1 minus 2 over 2. And w plus 1 minus 2w over 2. Common denominators, which is w minus 1 over 2. And this one here is negative w plus 1 over 2, which actually you can really simplify this, because you can write, like for example, you can take the negative out of this one. Like you can actually just take that, the negative, and that'll be w minus 1 over 2. And this will be w minus 1 over 2. So can you see how I did the same thing? So we can just write them as squared. We can write it like that. So negative w minus 1, 2 squared. You can just write it like that. And so that's minus w minus 1 over 2 all squared. Not bad, not bad. That is that looks perfect. That's your actual turning point. Then you can expand it if you want. I don't think it's yeah, let's expand it. Why not? Like, the 2 squared, this will become 4, but this leave as squared, because I'm not. Yeah, you don't think you need to expand this. It's too much work. Easy, so you can leave it like that. Let me write that nicely, and that is it. This is what your turning point is. What an easy, beautiful. Oh, what happened there? What an easy question mark that is. It's a very nice question for 2 marks. And then this is the last question. Now, it says hence. So hence means in using these here, or otherwise, or anything else. Basically, find the positive values of w where f of x and g of x has exactly 3 solutions. So basically, how they're equating those 2 functions? We're basically saying we want those intersections. Those intersections? We want the number of intersections to be 3. Only 3. How do we do that? Well, okay. Now, let's just equate those 2 functions. Like, how it was w squared x minus 1 squared. Let me write that down. W squared x minus 1 squared. Let me just double check. So w squared x minus 1. Is that right? Yes. And then equate it to g of x, which is x minus w squared. Alright, x minus w squared. Perfect. Now, if I bring that x minus 1 to the other side, better to do that than this whole here. Okay, done. We've got this. Now, when we solve this equation, yeah? Because how we've equated those 2 functions? We need to get 3 solutions only. Now, what we do is, remember how we, like last time, what we can do is kind of, because they have the squared here, we can just put them all in one like that. Get rid of the squares and just put them all in one like that. That's all on squared. And then get rid of that square by taking the square root. So plus 1 minus the square root of this, which is going to be w. Basically, in this case, w. Plus or minus w. Now, let's think about it here. What we can do is, this is so easy because, like what we did last time, how do you find a point of intersection between, like, this? We can, graph it, can't we, yeah? Let's graph it. Like, for example, if I graph this, like that. Actually, I'm going to put it like this so it doesn't really hurt eyes. So like that. Let's graph this. Like, can you see how when we're graphing this is actually really easy to graph? It's just a parabola, like w, and where the x-intercept is w, where of course w is positive. So if this is your 1, and this is your w, draw a positive parabola, like what we drawn last time. Okay. Something like that. And beautiful. So this is our parabola, and we draw the y equals negative w. So like let's draw that in purple. It's because w is positive, yeah? So let's look at the positive part. So positive is going to be something like this. That's negative y equals positive w. And y equals negative w, which is just something like this, you can say. Now, look, legends, there's a lot of ways you can get solutions. Like in this case, there's actually, just of the one I've drawn here, there's actually, you can see that there's only 2 solutions. Because can you see how this part's intersecting only twice? This is not, this graph, this line's not even intersecting, yeah? So that's, in this case, we only have 2 intersections. Of course, how do we make 3 intersections? There are many possibilities. Of course, you can kind of just take this graph and put it like this. Now, this is 4 intersections. Look, here, that's 1, that's 2, and that's 4. How do we get 3 then? Well, the easiest way is actually very easy. You take this over here and you just put it right in the minimum turning point, can't you? Yeah. And do you see that? That's just 1, that's 2, and that's 3. Do you see how we can guarantee 3 is just doing that? And so beautiful. So what that means is, look, for when you're solving this function, when we're when we're solving this, when it's equal to w, yeah, we need to make sure that we get 2 solutions. We get 2 solutions, yeah, when it's the positive w. So let's do that. So let's write this function, like this function over here. Okay, what's happening here? X minus w, x minus 1 equals the positive w, and let's do that first. So, you expand that whole thing. X squared minus x. Oh, so yeah, minus x minus wx, positive w equals w, and those w's just cancel out because they both have w's, equals 0. Now x is a common factor, so it'll be x minus 1 minus w equals 0. So we get x equals 0 as a solution, and x equals w plus 1. Perfect. Do you see this? So look, we already got two x values. These are our two x values. You know these for this one, these are so that one and that one. Those are our two x values that we have. Look, those perfect. And what we're gonna do is when we solve for the negative w one, so the same process but for the negative w, we need to make sure we only have one solution, not two solutions, just one, specifically one. Yeah. So what we can do is do this. So let's look at the same basically copy and paste that right over here. But now, of course, this is negative w, and do the same thing. Yeah, expand it. Well, x squared minus x minus wx. I don't know why I'm expanding it again, but equals negative w. So bring that. So what I'm gonna do is the x's put them all in one. So like negative 1 minus wx. And if you bring that w, it'll be 2w equals 0, like that. And then you can see that it's a quadratic, beautiful. And you remember what we want to do when we solve this, yeah? We specifically wanted to have one solution. Remember, we wanted to specifically have one solution, that one. So if we wanted to have one solution, how do we guarantee that when we solve this quadratic, we get one solution? We have to use the discriminant. And we need to make sure that the discriminant equals 0, because remember, when it's equal to 0, we get one solution. Of course, if it's less than 0, no solution. Greater than 0, it's two solutions. So what we want is specifically the discriminant to be this equal to 0. We want it to be equal to 0, so to get one solution, because that's what we want. So what's our b squared? It's just that negative 1 minus w all squared minus 4. A is in this case 1, and c is 2w equals 0. And of course you can expand that whole thing here, which is just like negative 1 minus w, negative 1 minus w. So that's like positive 1. Let's just expand it here. Yeah, like positive 1 plus w, positive w, plus w squared. That's positive 2w, positive w squared. Oh my, that's so ugly. Ugh. It's not ugly. It's just like it's a little algebra. Yuck. Okay, and then multiply those. It's minus 8w equals 0, and so we get w squared minus 6w plus 1 equals 0. And then guess what? We just solved this. We just solved this normally now. So we need to solve for w, which is just using again the quadratic formula, which is negative. So to get w, it's negative b, so it'll be positive 6 plus or minus b squared, which is 36 minus 4. A is 1, c is 1. What's 36 minus 4? That's 32 over 2a, which is just 2. And the square root of 32 is because you can write it as 6 times 6, 12. You can write it as 4 root 2. 4 root 2. And you can simplify that because the 2 goes into 6 3 times. And the 2 goes into 4 2 times. 2. And that's it. Now, is that your final answer? Be careful. Remember, going back to the same thing, w is greater than 0. Are these values? Of course, the positive one's positive. Like 3 plus 2 root 2 is positive. But what about 3 minus that 2 root 2? Is that positive? We gotta check. Okay, root 2 is 1.4 normally. It's around 1.4. So that's like, I don't know, like 2 point. I'm making it up like 2.8. Yeah, it's positive. 100% it's positive. Yeah. So both solutions work. Right, so those are your w. Those are your w values. Okay, let me draw them of color. Easy. So those are your values of w. Now, that is just like a long process. Now, by looking at the question, you can actually do it much more quicker. Let me show you this quick process. Well, we learned that, for example, why did it say hence? Hence means using your thing here, over here. Well, what could have done is, like, you know how this is our in this case, we know the coordinate of this is going to be this, yeah? Don't we? We know the coordinate of that minimum turning point is that. We know for a fact that what is the y value? What does the y value have to be for us to get, this line over here to intersect at once? We need the y value of this turning point to be equal to negative w. Isn't that right? The y value of the turning point, this turning point, to be equal to that negative w. Isn't that correct? So what we could have done is much more quicker, is we could have just took the y value over here, which in this case is that negative w minus 1 squared over 4. And we would have equated it to negative w, because negatives cancel out. And then that 4's here. I'm going to bring that 4 to the other side. Expand that. Equals 4w. and then bring that, what do you have? W squared, bring that 4w to the other side, it'll be that, plus 1, and guess what, legends? This would have been easier because this here just straight away gave us that quadratic that we just found all the way to here. You see that? So we could have solved it like that. But at the end of the day, all processes work at the end of the day. So yeah, I'm not gonna lie, what a beautiful exam. I actually love this exam. When I saw it, I was actually quite happy because it was actually nice and easy. It wasn't too hard. It was perfect, mate. So beautiful. I hope you guys enjoyed this video and it helped you with your studies, and good luck everyone, yeah? Take care of yourselves. Bye-bye.